Before we get into the beginning of Calculus 2, we want to spend a little bit of time reviewing a few topics from Calculus 1. In particular, I want to start by looking at integration by substitution, mainly because different teachers teach it differently in Calc 1, and I want you to see the way that I like to do it, just so you'll be used to my way when we get into it. So the first example you'll see in your notes is the integral of 6w squared secant w cubed dw. Now, the first thing you should always ask yourself when you get to an integration problem is it a straight integration problem? Meaning, you don't have to do substitution. Do you know a formula that you can just write down the answer without doing any work? So don't forget to ask yourself that. So many students will try fancy methods of integration when it turns out it's just a formula you already knew. And I would say a no here for a couple of reasons. One, it's not just secant w, it's secant of w cubed, it's secant of stuff. You have a product, but of course we can do some integration with straight integration with some products, like for example the integral of secant x tan x dx. That's a product, but we have a formula for it. So this one's rather complicated. Now again, there's only a finite number of things you would let u be here. I mean, what are some reasonable things to let u be? Never let u be W, is this W or an omega? That looks like an omega. Well, whatever. If you let u be W, you're just going to get the same problem back. Never let u be W. Well, what are reasonable things for u to be? W squared, W cubed, secant W cubed, the whole thing. I mean, there's only a finite number of things to try, gang, so you just pick something and try it. But a guiding principle, which does not always help you, is look for things that are derivatives of other things. Because once you choose u, remember you compute du. So if you let u be secant w cubed, when you take du, you're going to get a secant tan, and there's no tangent, right? So that you can try to eliminate some things that way. So what's a reasonable thing to pick here? I'm going to let u be w cubed. And that eliminates one of the issues I mentioned before, right? It's not just secant w, it's secant of stuff. If you let u be w cubed, it's secant of u now, and you don't have your stuff. Now, why is this reasonable to do? Because if you take du, the derivative of w cubed is 3w squared dw. Now, some professors here like to do one thing. I like to do this. I like to match what I have here with what's in the problem, okay? So I have a 6w squared dw in the problem. I have a 3w squared dw on this side, so I'm going to multiply both sides by 2. Right? So my du step here, I'm multiplying both sides by 2, so then this matches what I have in the problem. That's what I like to do. If you wanted to, you could have pulled the 6 out front and just pretended it wasn't there. But in that case, I would have had a w squared, and I would have multiplied both sides by a third. Okay. Either way, you're going to wind up with this in the long run. Okay, now let's do the substitution. It's a good idea to substitute for this first. Don't substitute for the u first. There are certain types of problems where the du and the u are the same, like in an e to the x problem, and if you replace every e to the x with u, you may not have one left over for the du. So always get in the habit of doing this, substituting for that first. And make sure you substitute for everything in the original problem. Okay? So instead of 6w squared dw, that gives me 2 du. So I'm going to have 2 du here, but you're going to have a product, so I can pull the 2 out front. Now keep on, what did I get rid of? Just the 6w squared dw. So what's left to substitute for? I still have secant w cubed. I need to write that in terms of u's, but w cubed is u. So I have secant u. And this is something that we know how to integrate from Calc 1. Okay. So I'll just bring down the 2. Now the question is, since you've had 3 weeks to review your integrals, because I sent you that formula sheet to be studying, do you know off the top of your head the integral of secant u? That's the question. Okay? The integral of secant u is natural log absolute value of secant u plus tan u. This is an indefinite integral, so don't forget your plus c. Okay, I always want to see your integration step. Do not integrate and back substitute in one step. I want to see the integration step with the same variable here, then you can back substitute. 2 natural log absolute value, of secant, what was u, w cubed, plus tangent w cubed, plus c. And there's your answer. My guess is the hardest part of this problem was going from here to here because you don't remember your formulas. You have to know your formulas from Calc 1. I'm not giving you a formula sheet. You need to learn all those formulas. Okay. Let's do another one here. It says the integral of 9x cubed plus 5x all over 9x to the fourth plus 10x squared plus 3 dx. Okay, so we have a rational function here we want to integrate. So where do we begin? Ask yourself, what do we do first? What's the first step? And if your first reaction was let u equal, not yet. The first step is ask yourself, is this a problem that you can do with straight integration? And it doesn't look like it. Something to keep in mind that I'm sure will pop up later that you've seen in Calc 1. If you're integrating a rational function and the degree of the numerator is bigger than or equal to the degree of the denominator, common thing to try is long division. Okay, so keep that in mind. It pops up every once in a while in calculus, 1, 2, 3, when you're trying to integrate, just if you have a rational function and the degree of the numerator is bigger than or equal to the degree of the denominator, try long division first, unless something else is easier that's clear to you. Okay, so I know it's not straight integration. I mean, it's a polynomial over polynomial. One special case though, if you have a rational function with say a single term in the denominator, just divide, right? Break it up and divide each term by the single term. That's easier to do too. Okay, so what's something reasonable to choose for u? Well, you probably remember from Calc 1 when you have rational functions, a common thing to try was let u be the denominator. That's not always, what you do, but okay, let's take du. I get 36x cubed plus 20x dx. Now, does this look like we're on the right track or not? Well, it doesn't match the problem here, but notice what I have here is 4 times the numerator. So if I multiply both sides by 1/4, I get 9x cubed plus 5x dx, and now this matches what I have in the problem. And remember, when you're doing a substitution problem, the du has to wind up in the numerator, out here. It can't be in the denominator. Okay, let's do the substitution. Always substitute for this first. So 9x cubed plus 5x dx is a 4th du. I'll put the 1/4 out front. You can put the du in the numerator if you want, but I'll just write it out there where I usually do. Now what's left to substitute for? All I have left to substitute for is the denominator, which was u. Okay, I gave myself too much room here, but there's 1 over u. Okay, now you ask yourself, what's the integral, the antiderivative of 1 over u? So I have my 1/4 out front, and what's the integral of 1 over u? Okay, remember that's the natural log absolute value of u. Don't forget your plus c, and then you back substitute. What was u? 9x to the 4th plus 10x squared plus 3 plus c. Notice on this answer, if you accidentally didn't put absolute value signs and you put parentheses instead, you'd still be correct because 9x to the 4th plus 10x squared plus 3 is always positive. So if you didn't put the absolute values on it and put parentheses instead, you still get it right. But I would just get in the habit of having those absolute values when you integrate 1 over u. So that one's not too bad. Okay, next I want to do a special case of substitution. My example here is e to the 4q plus 7 dq. I'm trying to use a lot of different variables here just so you get used to it. Okay, so let's do this now. If you had had me for Calc 1, which none of you did, I explained this in Calc 1, and we use that for the last part of the semester to save us a little bit of time, but that's why I'm showing it to you here. So in Calc 1, for you probably just did it with the substitution, so that's what I'm going to do here. Now what's the logical thing to let u be here? It's not a straight integration problem. That's what I'm teaching you. What I'm teaching you how to do is be able to do this as a straight integration problem, so then you don't have to do substitution anymore. So if you let u be 4q plus 7, notice it's e to the stuff, okay? That's why I'm letting u be 4q plus 7. Now notice 4q plus 7 is a linear expression, like y is mx plus b, right? It's 4q to the first plus 7, right? So this is a linear expression. So I'm teaching you how to do substitutions with that are linear substitutions. Okay, let's take the du. Du is 4 from here, and then dq. Notice I don't have a 4, sitting out here in the problem. I try to make this match what's in the problem. I don't have a 4, I just have a dq, so I'm going to multiply both sides by a fourth. Okay, now let's do the substitution. Well, always substitute for the dq stuff. dq is a fourth du. That takes care of the dq. And then what I'm left with is the integrand here, e to the 4q plus 7. Well, 4q plus 7 was u, so that's just e to the u. And what was the integral of e to the u? Well, that was easy, that's e to the u. Don't forget your plus c, and then we back substitute. Oops, not d. Plus c, easy. That's not our problem. Okay, so that one's straightforward. Okay, I'm gonna try to leave that up here because I want to look at these this one and this problem we just did and the next one and see where we are. Let's do the integral of tangent of 13 minus 7y dy. Okay. Again, this is not a straight integration problem because it's tan of stuff, not just tan of x. So let's let u be 13 minus 7y. Notice this is a linear substitution, right? It's written up, so this is like mx plus b, and this is like b plus mx, but it's still linear in y. Okay, now what's du? The derivative of this is negative 7 dy. I don't have a negative 7 in the problem, so let me multiply both sides by negative 1/7, just to get dy. Now we're ready to substitute, so I'm going to replace dy with negative 1/7 du, and I'm left with tangent of u, aren't I? That's it. Okay, and now the question is, what is the integral of tangent u du? Again, is this one you know off the top of your head? If not, you've got to learn those formulas. Do you know it? Okay, it's minus nat log absolute value of cosine u plus c. I had to make sure I knew it before I yell at you. Okay, so the negatives here multiply to 1, so I get 1/7 nat log absolute value of cosine u, which is 13 minus 7y. Let's see, there we go. Okay? Okay, so both of these were linear substitutions, right? U is 13 minus 7y, u is 4q plus 7. Now, I want to be able to do these without doing all this work, okay? Because what happened when we did the linear, think about what we did here. Here was my linear, u is linear, take the du, and I just wanted the d cubed. Notice I wound up dividing by the slope, right? 4 is the slope of the linear expression. What was the slope here? -7. Notice I wound up dividing both sides by -7. Okay? And notice that just stayed out front here, right? Now granted, the negative disappeared because this, but I mean, still basically sitting out front. Same with the fourth here, right? Right? So whatever the slope is in your substitution, you want it with that, you know, the 1 over that out front. Now what about the rest of it? Okay, let's go back to this. What did the integral of e to the linear turn out to be? Right? Notice it turned out to be, you know, e to the, it was e to the u. Right? Once we did the substitution, that just turned out to be like an x, right? The integral, this turned out to be e to the u, which was the linear, e to the linear. We know the integral of e to the x is e to the x. Notice how do we get the integral of e to the linear? It's e to the linear, because that's, you know, the integral of e to the x is e to the x. The integral of e to the linear is e to the linear, but then you have to adjust for that slope, 1 over the slope. Now what about here? Right? What's the integral of tan of x, just tan of x? It's minus natural log absolute value of x, of cosine x, right? So it's exact same formula, and notice what do we want to putting in u? For linear. So if you just treat this as plain old x, okay? Let me do that again here, right? What's the integral of e to the x? E to the x. The integral of e to the linear is e to the linear, adjust for the slope. What's the integral of tan of x? Minus natural log absolute value of cosine x. So what's the integral of tan of linear? Minus natural log cosine linear. Adjust for the slope. Okay? So whatever rule you use for plain old x, use the same old rule, but replace the x with the linear expression. And then adjust for the slope out front. 1 over the slope. Okay? That's how you do all linear substitutions. Okay, so if you're still a little vague, the next problem uses a whole bunch of them in one problem. And you'll see why it's handy to know this little procedure instead of working it all out. So we have the integral of e to the 3x minus 4 plus sine of 2x plus 3 plus 2 to the 3 minus 8x plus cosecant of 6x minus cotangent of pi plus 2x dx. Okay. So if this were just a problem in Calc 1, it'd be 1, 2, 3, 4, 5 different substitutions. Let u be 3x minus 4, and then 2x plus 3, 3 minus 8x, 6x, and then pi plus 2x. Now I want you to notice all those substitutions I just mentioned are all linear. mx plus b, that's b plus mx, same thing. mx, b plus mx, they're all linear substitutions. So you can do what I just did on that problem. This is now a straight integration problem. You do not have to write out a substitution. Okay? Okay, so let's see if we can we'll do the first two together, and then I'll have you try the others. Okay, so again, this is e to the linear. Well, think of that whole thing as just like x. So what would the integral of e to the x be? The integral of e to the x is e to the x, so the integral of e to the linear is e to the linear. It follows the same rule as the plain old x, but you have to adjust for the slope. The slope of the linear expression is 3, so you have to multiply by 3. That one works just like the one we did a little while ago. Okay, now let's move on to the next one, but this is sine of linear expression. Well, what if this were sine of x? If this were just sine of plain old x, what would the integral be? Okay, what's the integral of sine of x? Well, it's negative cosine x, isn't it? Remember, the derivative of sine x is cosine x. The integral of sine x is minus cosine x. Right? So the integral of sine x is minus cosine x. So the integral of sine of linear is minus cosine of the linear. But then what do you have to do? You have to adjust for the slope on half. Right? Do you see what I'm doing? Just replace the linear expression with just x. figure out the integration rule with plain old x, replace the x with the linear again, once you figure that out, and then adjust for the slope. Okay, so pause the video and see if you can do the other three. Hopefully you know your integration rules. I hope you realize what I've done in this first section of notes here is put a whole bunch of integration rules from Calc 1 to make sure that you're going back through them. So pause the video, see if you can do the other three, and then press play again, and then I'll finish it up. Okay, so we just move on. Now what is, right, we want to integrate 2 to the linear. Well, what's the integral of 2 to the x? Do you remember the integral of 2 to the x? Okay, well the integral of 2 to the x was 2 to the x, so it's going to be 2 to the linear, times 1 over the natural log of the base 2 here. And then we have to adjust for the slope, right, minus 1. Okay, remember, the integral of 2 to the x dx is 2 to the x times 1 over natural log of 2. That's the rule I'm using. Okay, so if it's linear, you just put the linear expression there, but then you have to adjust for the slope, which was negative 8. Okay, let's keep going. Cosecant of linear, well, you just have to ask yourself, what is the integral of cosecant x? We just did the secant x earlier. The integral of cosecant x is minus natural log absolute value of cosecant x plus cotan x, but instead of x, you put the linear expression, and then you have to adjust the slope. Now I know we have the 6x and 6 both places, but you only adjust for the slope once. And then the last one, minus cotan pi plus 2x, again this is a linear expression, so you have to ask yourself, what is the integral of cotan x, right? So the integral of cotan x dx, do you remember? It's natural log absolute value of sine x plus c. So the integral of minus cotan of pi plus 2x, so I'm going to carry the negative down, negative. Then it's natural log absolute value of sine of, instead of the x, you put your linear, and you have to adjust for the slope, which here is 2, so it's 1 and put your plus c for the entire problem. Okay, so you are welcome to do this on any problem in the course that has a linear substitution. So every linear substitution problem is now a straight integration problem. So when I say, is this a straight integration problem and it's a linear substitution, the answer is going to be yes, and I'm just going to do what we did here. Okay? Okay, so now let's go back to some theory. That was just practice with integration and trying to teach you linear substitutions to try to save you some work later. Okay, right. Okay, so let's go back to rectangles and areas under curves. So remember we had this generic picture. That's my standard generic picture. Okay, and typically, well, we typically said let's cut this thing up from A to B. So I'm trying to find the area under the curve from A to B. I'll just call my curve f of x, like we always do. And what we did, do I want to use an equal partition? What we did is when we first did this, we chopped this up into equal subintervals. I'm going to go ahead and do that just to save ourselves a little bit of notation. So I'm going to, okay, so remember we found this delta x, which we computed as b minus a over n, where n is the number of rectangles. So if you think that this makes sense, it's b minus a is that distance. If we want to chop it up into n equal pieces, you're going to divide that distance by n. So that's delta x. Again, you don't have to make this an equal partition, but I'm going to do it here just to make it easier. Okay, so we called this x naught, and if you moved over delta x, we call that x1, right? The delta x is the width here of the rectangle. So move over another delta x, you're at x2, and you keep going. B we called xn, and the point right before is xn minus 1, so there's another delta. So you have n intervals here. Notice what's n times delta x? It's b minus a, right? So if you have n of the delta x's, you get the entire interval. Okay, so then what we do, we made rectangles. So how'd you make a rectangle? So I'll do this with right endpoints. You could do it with left endpoints, you could do it with midpoints, you can do it with anything. But in calculations, you typically did the right endpoints. Okay, so for the first interval, go to the right endpoint, go up until you hit the graph, and then make that the height of the first rectangle. There's the base, that's the height, so I have to move over this way. Okay, go to the second base, right endpoint, go up till you hit the graph. That's supposed to be a horizontal line. And you keep going, last interval, go to the right endpoint, go up till you hit the graph, make that the height of the rectangle. Okay? Okay, so what's the area of the n rectangles here? Well, the area of a rectangle is base times height. Well, the first base is delta x. Now, what's the height of the first rectangle? Well, the height is given, it depends on what x1 is, but notice it's the y value of the x1. Notice this point's on the graph. What are the coordinates of that point? x1, f of x1, right? That's x1, f of x1, right? So the height of the rectangle is the y value at x1. So it's f of x1. Now that's the area of the first rectangle. Now let's move to the second one. It's base times the height. Well, what's the height of the second rectangle? Well, it's the y value at x2. Notice that this point is on the curve, and so that's the point x2, f of x2. And then if you keep going, what's the area of the last rectangle? The base is delta x, and the height of the rectangle is f of xn, which is b, but I'm just going to write x. Now we can write this in a shorthand notation with summation notation. Every single term has a delta x. Every single term has an f of something. So we're summing up f of something delta x. Well, what if we let I be our indexing variable? What is I running from? I is going from 1 to n. And that's x of I, right? When I is 1, you get f of x1 delta x. When I is 2, you get f of x2 delta x. Dot, dot, dot. When I is n, you get f of xn delta x. Okay? All right. Now notice, the area of the rectangles here is not the area under the curve. Right? Notice the area of the rectangle here, notice I'm counting that area in the rectangles that's not part of the area under the curve. Here, I'm not counting that as part of the area of the rectangles, but it is under the curve. And this one here is same as this one. The area of the rectangle is counting that, which is not under the curve. So remember, the area using rectangles is an approximation of the exact area under the curve. Okay? So this expression right here, going to part B in the notes, right? This is called a Riemann sum. The sum I equals 1 to n of f of xi delta x. Okay. Now, if I had used an unequal partition here and not chopped this up into equal pieces, I'd have delta x1, delta x2, delta xn. I'd just have a delta x sub I. That'd be the only difference if I hadn't used an equal partition. Okay? So that's a Riemann sum. Again, this is basically the area. The Riemann sum is just the area of the rectangles, and the way I've drawn the picture. Okay. Now, if you want to actually get the area under the curve, you'd have to eliminate these extra, the areas that we're counting and not counting. It's extra area into the rectangles here we don't want, and here we didn't have enough. Right. So remember, the idea is, what if we took double the number of rectangles here? Well, if I'd chopped that up here, notice that would have been a rectangle, and that would have been a rectangle, and some of that extra area I counted, I'm no longer counting, right? Same thing here. Likewise here, I wasn't, I wasn't counting enough, right? If I chop this up into another piece, it'd be here, and then here, right? So some of the area that I wasn't counting, well, yeah, here, this is better. So that's not really changed that much. But this one here, notice I'm counting that under the rectangles that I wasn't counting before. Okay, so I've helped that. So the idea is that the more rectangles you pick, you get rid of it. You get rid of the exterior you don't want, and you add in the area that you do want. Okay, so what we want to do to get in the area under the curve, we want n to go to infinity. Okay, so we took the limit as n went to infinity of the Riemann sum. Right, that's the motivation to do that, to try to get rid of the extra area we don't want to count, and to add an area that we should have been counting. Okay, so this was the Riemann sum. If you take the limit of the Riemann sum, what did that turn out to be? That was the definition of the definite integral. So throughout the course, when I ask, what is a definite integral? It's the limit of a Riemann sum. That's the definition of the Riemann sum, of the definite integral. It's the limit of the Riemann sum, like this. Okay. Again, I derived this with an equal partition. Remember in Calc 1, if it wasn't an equal partition, you had to say the limit of the norm goes to 0, if you remember that. Okay. What is a definite integral? The limit of a Riemann sum. So when you first were doing these, computing definite integrals, you only did it for polynomials of degree 3 or less, because those are the only formulas, summation formulas we had. But you took the limit of the Riemann sum and you worked this out, and your Calc 1 teacher probably filled up the entire board to work that out. Okay? And you did sections 4.2 and 4.3 working on those. Okay? Okay, then you learned, this is part C here, the fundamental theorem of calculus. So we were trying to compute, before that section, you were computing these definite integrals by either using geometry or taking the limit of the Riemann sum where it was a polynomial of degree 3 or less. Okay. Then the fundamental theorem of calculus said there's another way to compute definite integrals without doing the limit process. And what did that say? It said that capital F be an antiderivative of big F. So find an antiderivative, plug in the top endpoint, plug in the bottom endpoint, and subtract. Okay? Now I want you to realize this is not the definition of a definite integral. I'll say, what is a definite integral? And find an antiderivative, plug in the endpoint, subtract. No, that's not what it is. A definite integral is the limit of a Riemann sum. The fundamental theorem of calculus tells you how to compute definite integrals without doing the definition, without using the definition, the limit of doing the limit. Okay? So the fundamental theorem of calculus is a great device because it tells you how to compute definite integrals without using the limit process. Now, what's a limitation of the fundamental theorem of calculus? You have to know an antiderivative. If you don't know an antiderivative of little f, you can't use the fundamental theorem. But what could you do? You could approximate, right? You can always make a computer program to chop up an interval into 1,000 pieces, compute all the delta x's and f of xi's, and add them all up, right? So if you let n be large, this is a good approximation. So, but if you don't know an antiderivative, you're not going to get very far with that. Okay, so that's what the fundamental theorem of calculus is. All right, it tells you how to compute definite integrals without using the limit process. Okay, it's just like in Calc 1. I'll have students that have had Calc 1 before, and I'll say, what is a derivative? Bring down the power, subtract 1 from the power. No, that's not what a derivative is. That's a computational formula for one certain type of function, right? Just like this. This is not what it is. It's a computational formula. Okay, so let's do an example of a definite integral now. And I didn't go into this, but remember, I drew my picture a second ago with a curve that was above the x-axis. Remember that the definite integral represents a net, a net area under the curve, right? So for example, the picture I had before, the definite integrals would be positive. But on the other hand, right, if you do the integral from 0 to 2 pi of sine x dx, what is that answer going to be? Well, here's 0, here's 2 pi. A definite integral will treat a graph that's above the x-axis as, area, but a curve below, when the curve drops below the x-axis, it treats that, I will say, as a negative area. And why is that? Because remember, the definition of the Riemann sum, right? If you when you're chopping over here, what's f of xi going to be? It's going to be negative. So it's going to take a negative number times the base times the height of the rectangle. That's the base. The height here is actually negative. Okay? So what is this going to be? It's going to be 0 because the positive area and the negative area cancel each other out. So be careful about saying the definite integral is the area under the curve. No, I think of it as a net area. Okay, so that'll probably come up throughout the course too. Okay, let's do this last example in this section. Compute the integral from 0 to 2 of m squared plus 3m plus 5 to the 4th times 6m plus 9dm. Wow. Okay, so is this a straight integration problem? Yes, it is. You don't want to do it that way, but it is. You could it's polynomial times a polynomial. You can multiply this whole thing out, get a long polynomial of what, degree 9, if I'm doing that right, and then integrate term by term. So you could do it with straight integration, but I think we should at least try a substitution. And what makes this one a difficult straight integration problem? Because of 6m plus 9? No. It's because of the fourth power. If that fourth power weren't there, it'd be easy to multiply and integrate term by term. It's the 4 that's the problem. So we want to get rid, that's the stuff. It's stuff to the 4th that's the problem. Right? So if we get rid of that stuff, let me replace u with m squared plus 3m plus 5. Right? Again, you have to try something. Again, there's only a finite number of things to try for you in this problem. 6m plus 9, m squared plus 3m plus 5, m squared plus 3m plus 5 to the 4th, or the whole thing. I mean, there's only four things I mentioned that are reasonable to try. So let's take du, that's 2m plus 3, 2m plus 3, dm. Now, that doesn't match what I have in the problem, but we're off by a multiple of 3, so I'm going to multiply both sides of this equation by 3. Right? So now this matches. Let's do my substitution. If I substitute for that first, that becomes 3 du. 3 du. And I've already substituted for that. This is all that's left, and that's u to the 4th. Okay, now look at that and think about it. How do you feel about what I have written there? I hope you realize this is not the same as the original problem. This is a definite integral. This is an indefinite integral. They're not the same thing. Because what? What's a definite integral? It's the limit of a Riemann sum. What's the definition of an indefinite integral? It's the set of all antiderivatives of the integrand. Right? Those are two completely different things. Right? Limit of a Riemann sum is a number if it exists. And this is an indefinite integral is a set of all antiderivatives of the integrand. It's a set of functions. Those are not the same thing. All right, now what's the problem here? I need limits of integration. All right, so let me put 0 and 2. How do we feel about 0 and 2? All right, that's not right. M goes from 0 to 2. This is not an integral with m. This is an integral with u. Now, I like to change my endpoints. Some people are resistant to do that. I like to change endpoints. Okay? So, but it's very easy, right? You just use this right here. This is how m and u are related. This is m when this is m is 0. This is m is 2. When m is 0, what's u? 0 plus 0 plus 5. U is 5. Now, if the number I plugged in 0 to get m, you put it in the same location, even if the numbers get bigger or smaller, right? So when m is 0, u is 5. So 0, 5. And then when m is 2, what is that? 2 squared, that's 4, and 5 is 9, and 6 is 15. Okay, let me check myself. So when it's 2, you get 2 squared is 4, plus 6 is 10, right, is 15. Okay. Now, if you change the endpoints like I did here, you do not have to go back to the original variable m. I wouldn't. Right? So now we just go ahead and we integrate. The integral of u to the fourth is u to the fifth over 5, evaluated from 5 to 15. Remember, that's what the vertical line means. Plug in the top number, plug in the bottom number, and subtract. That's your f of b minus f of a. Okay, so I'm going to write the fraction as 3/5 here. That's 3/5, 15 to the fifth minus 3/5 times 5 to the fifth. Okay. If we want to get a I got 453,750. Okay. Always double check me. Don't believe me. Okay, so if you absolutely positively, I shouldn't give you this option, but if you absolutely do not want to change your endpoints, okay, let me show you what you can write. Because if you're going to go back to the original variable m, there's no point in finding the 5 and the 15. Okay, so at this point, what could you write that I'd be okay with, right? If you knew you were going to go back to m's, you would get down to this point like we had before, right? Right? Okay, let me get rid of this. Okay, so you were here. But you can't write 0 and 2. Even though you're going to go back to that, you don't write 0 and 2 because that's just a lie. That's not right. Okay? If you want, I'm perfectly fine if you put a and b here. That tells me you know they're not the same thing. And then here you would say 3u to the fifth over 5 from a to b. Then when you back substitute to m's, you're going to have 3/5 m squared plus 3m plus 5. I notice I just replaced u with what it was. That now is from 0 to 2. Okay, so now as soon as you go back to m's, you can put the endpoints you know you're using 0 and 2. Now, why you would want to do this, I do not know, because what's your very next step? Your very next step is you're going to plug the 2 into that. And what are you going to get? You're going to get the 15 I got before. Right? You wind up plugging that into that expression anyway. When you plug in the 0, you're going to get the 5 I got. So these are the numbers you're going to get. It doesn't save you any work. That's why I don't understand why students are so resistant to changing endpoints, because you're going to do that step anyway. Right? You're going to plug in 0 and you're going to plug in 2, which is exactly what I did. Then you don't have to worry about this notation issue. Again, notation is important, and this is not, developmental math. This is Calc 2. You should be worried. Your notation should be pretty good by now. Okay? Okay, so there's some review from Calc 1.